So today we are continuing with our talk on organic chemistry, and I'm starting with this video that is uh, it's a review for us for the structural displayed and something called the skeletal formula. Now the skeletal formula is not something that we need to be concerned with, but the molecular structure and displayed formula are. Okay, so let's just take a quick view of this video for to jog our memories and better understand the different types of structures, or drawing out the structures, and then we can continue with talking about alkenes. Here we go.
There are a number of different ways in which we can represent a molecule in organic chemistry. We've got the molecular formula, structural formula, displayed formula, skeletal formula. You need to be clear about the differences between all of these. I'm going to use ethanol as my example. Ethanol has the formula CH3CH2OH. And this is its structural formula because I can see the way that the atoms relate to each other. I've got a CH3 group, a CH2 group, and then an OH. Molecular formula would be C2H6O. It just lists which atoms we've got and the number of each that we've got. It doesn't show me how the atoms relate to each other, because C2H6O could be not an alcohol, but an ether. It could be this molecule here.
Now, just to pause there and don't worry about what an ether is, and we're going to cover alcohols later, right? So don't worry about the type of compound they're talking about. Just focus on molecular structure and displayed formula.
So structural formula is far more useful than a molecular formula. Sometimes we like to display the bonds, and that would be a displayed formula. So carbon, carbon, hydrogens, you need to draw in the hydrogens, oxygen, hydrogen. That would be a full displayed formula, although often we see it represented with the functional group, not showing the bonds between, just OH on the end there. So there's my displayed formula. Skeletal formula are essentially the shorthand, and these are very, very useful. We're going to use them a lot between carbon number. I don't usually, nothing else between the atom and the function. See, the structural carbon, that will be hydrogen to a branch, so there'll be a shorter bond
this is another example,
to an oxygen. Let's have a look at a slightly more complicated molecule. How about CH3, C, CH3, OH, CH3. So we've got a structural formula.
Remember we did isomers and we had the CH group going around in places, right?
Yeah.
So this is some form of isomer.
Formula for a molecule, what does it look like? Well, I can draw it as a displayed. So carbon, carbon. I've got a side group here, carbon. That carbon is also bonded to an oxygen. Oh, my pen's not working. And another carbon. So those would be hydrogens. In terms of skeletal formulae, my longest chain.
Okay, so again, right, the molecular formula for this guy would be C4, because you've got 4 carbons here, and H, 1, 2, 3, 4, 5, 6, 7, 8, 9, so you've got 9 hydrogens, so C4H9 and OH. Right, that would be the molecular formula for this guy. The structural formulas, as you can see, right, so each part is written out, right, as it bonds. So first comes the CH3, next comes the carbon. The carbon has a CH3 side group, so that's given in brackets. It also has an OH group, so that same carbon has an OH group, right? And then at the end you've got another CH3, and so you can use this to very accurately draw a displayed formula, right, for a very accurate representation of what that molecule would look like. Let's see if this
is else. 1. I've got
So we're not interested in the skeletal
If
formula.
practice has been useful, hit the subscribe button, the effortless way to support.
Right? Does that help with your review? Right? Just to jog your memory. You know, we did something like this once upon a time.
Yeah.
Yes. Assalamu alaikum.
Alaikum assalam. Okay, you guys can see the whiteboard. So, right, that's what we did the last time. Talk about how to obtain alkenes. Then we talked about structural formula and displayed formula, and then we went into the realm of isomers. Right. So hopefully you guys remember this. Some of this you were making notes. And so today we will be continuing with our talk on alkenes. Okay, so we can have structural isomers and alkenes. So to pick up from where we left off, right? This is a good point. So a structural isomer is one where the groups of atoms are moving about. If in case the particular isomer involves the functional group of that molecule, then that is called a functional group isomer, right? So let's see how we have structural isomers in alkenes. And so the example is of butene. Do you guys remember what the general formula for an alkene is? Anyone?
Was CT.
C? Not C2. C, let's go with CN.
H2N
2N. Anything else? No.
plus 2.
No, that's for alkanes, right? So CnH2n is for alkenes. And for butene, what would be the value of N? What number would it be?
Uh,
How many carbons in a bute molecule?
2.
Oh, come
No,
on.
wait. No, not 2. 4.
Yes. Right? So you got C4H8. Now, how can you draw this out? You can draw it out the simple way. Oops, too many bonds. Okay. And then you put in the hydrogens. So this is how you would normally draw a butene molecule, right? Now, what if we go about and do this? Now, in terms of molecular formula, are these two molecules the same? Are they both C4H8?
Which one?
Both of these.
No.
They are the same.
So we count the carbons and the hydrogens.
Carbons are same.
And hydrogens?
Yeah, okay.
Right, so they're both C4H8. And so, right, if you want details about the molecule of the molecular structure,
Though, okay, continue.
the molecular formula is not going to tell you much about that, right? Both of these are C4H8. So these are isomers of one another. Why are they isomers? Because you got 4 carbons and they're all like, chain. There's no side group over here. Okay, so no side groups like anything we talked about over here. Right, it's a straight chain. The only difference is that the double bond, instead of coming right at the end, it's coming in the center. Now how, right, this molecule is called but1ene. How did I get the 1? Right, so I'm numbering the carbon molecule at which double bond is formed. How do I know which one to count from? I could go 1, 2, 3, 4, and so this would be but4ene. But that's not how we do it. Right? The numbering starts from the carbon molecule that is closest to the functional group. Okay, so when we talked about all these isomers over here with alkanes don't have a functional group, right? So technically, I mean, you could start counting from anywhere. But when you got, right, a functional group, and the double bond is the functional group for the alkenes, then you start counting from the carbon that is closest to the functional group. And so you could say, well, it's but2ene. Well, yeah, you could say that, but 1 is better, right? It's associated with the first carbon. So this is but1ene, all right? Or in other words, the regular butene that we're talking about, right? It's that. Why am I calling it but1ene? To compare it to this guy, right? To in fact not compare, but to contrast it from this guy. What would this be? So it has 4 carbons, it has a double bond, so it's an alkene, and it's a 4 carbon alkene, so that's a but. Now what number would I put in here? Can you guys tell me based on what I just explained?
1.
Is
Right.
the double bond with the first carbon of the chain?
It's on the second carbon.
Right. So you start numbering this 1, 2, 3, 4. And you'd go, well, why did you start from the left side? Oh, well, we can do it from the other way around, right? 1, 2, 3, 4. In this case, it doesn't matter because it's smack center. And both cases, whether I number it from the left or the right, it's giving me the second carbon, right? So it's but2ene. So it is a structural isomer of butene, where the 2 is representing the carbon-carbon double bond, right?
Yeah.
So is this clear?
Yes.
Yes.
Okay. Now, if this were a longer molecule, right, then the numbering would have mattered because for example, let's say it was, right, a pentene molecule, right? I'm just drawing the carbons. So if I started counting from like 1, 2, 3, 4, 5, and so this would be a pent2ene. But if I started counting from the right side, 1, 2, 3, 4, 5, in that case, I would have named this pent3ene, right? Now you would say, well, either are correct. It just depends on where you're counting from. No, right? Because the guidance is that you number the carbons that are closest to the functional group, and so the closest to the functional group is when you start counting from the left. And so the name you would give this molecule is pent2ene, not pent3ene.
Okay.
Now, right, we have our molecular formula, we have our displayed formula, right? For both of these are isomers. What would the structural formula for this be?
CH3.
Let's start from the, we numbered from the right
Oh,
side.
okay. Yeah.
So let's start from there. What do we have? We have CH,
2.
2.
Double bond sign.
Good. And then?
CH1.
You don't write 1, you just write
Uh,
CH. Then
so do you want me to continue or do
no
you
no
want
no 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 carry on, carry on.
CH2
Hmm.
and CH3,
CH3.
with the rest of them being single bond and all
Well,
of them.
you don't need to highlight the single bond. You could write it like this. It's not wrong. You could do CH2, CH, CH2,
But
CH3.
it doesn't need to be
Yeah,
written.
yeah,
It's
but these guys don't need to be, the single bonds don't need to be highlighted. It's sort of understood that the least you would have is a single bond,
okay.
right? But it's a double bond, you need to highlight, oh, there's a double bond. What
Okay.
would be the structural formula? Yes, for this guy, butene. So yeah,
CH3,
CH3,
CH with double bond,
mm,
CH1 with double bond,
CH,
and double bond
double bond before or after?
after,
Okay,
and then another CH1, and then
don't say,
CH
don't say CH1, just say CH,
CH3.
right? And you can see now, right, comparing these two,
Am I
right?
correct with structure form?
Yes, right. And
Okay.
so if I take a look at the structural formulas, are obviously different for both of these, right? And I can use these to very accurately draw out the displayed formula, even though the molecular formula is the same, right? But again, it doesn't tell me much. It just tells me the total number of carbon atoms and total number of hydrogen atoms, and it tells me nothing else. Okay.
Okay.
Okay. Now just one more thing, right? Again, this is not clear when we talk about when we talk about butene, but the pentene example I gave you, right? So we did pent-2ene. So this is C and double bond, and then C, and then C. These guys got 3 carbons. These both have, sorry, 3 hydrogens. Both of them have 1, and this guy has 2, and then 3. Okay. Then I have 3 and 1 and 1 and 2 and 3. Is there a difference between these two?
Mm,
Aram,
Yes.
is there a difference between these two molecules?
yes.
What's the difference?
Hydrogen
Hydrogen?
Double.
and the double covalent bond.
What's the difference? Is the position different?
Yes.
How? What's the position of the double bond over here? To which carbon will you attribute the double bond?
Second.
Okay. And over here?
Third.
No,
Oh, second.
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 it's the same thing. Why? Because I just told you, you start counting from the carbon that is closest to the functional group. The double bond is the functional group. And so for this one, I'd start counting from the left side. And so I'll still get the second. From this guy, I'd start counting from the right side. And I'd still get the second. Now, this might be considered something called a stereo isomer, but again, right, that's not part of the syllabus. Why am I highlighting this? Because, right, so to sort of make it easier for you, that, oh no, I have to draw it from the right side only. No, if a student ends up drawing it the other way around, as long as the position of the double bond or whatever functional group it is correct in terms of the carbon number to which it is attached, right? If the overall structure of the molecule, even if it's sort of mirror image, right, like you can put a mirror over here and this is what you'd see, right? But technically it's the same thing, so you can draw it either way as long as, right,
Okay.
the position is the same in terms of the numbering of the carbons.
Okay.
Okay.
Yeah.
Now, obviously, we can go into other examples, but I'm moving on for the time being. Now, reactions, right? Or as the book dubs it, the chemical behavior of alkenes. So the main type of reaction, so alkene reactions, and the main type of reactions that alkenes undergo are called addition reactions. And what happens in these is, right, molecules, I mean atoms, not atoms, or molecules are added across the double bond, in which case the double bond is broken, right, and two single bonds are formed. So how does this work? The first type of addition reaction is called hydrogenation. Now, guessing from that name, what do you think is being added to the alkene?
Hydrogen.
Hydrogen. Right? And so let's take a look at the example of ethene plus hydrogen. Right? So you've got CH4 and you've got H2. What do you think you're going to get? The hydrogen is being, the double bond is being broken and two single bonds are being formed. So what are you going to get? Is the number of carbons going to change?
No.
No. So you still have two carbons, right? The double bond is gone now. So now you only have a single bond between the two carbons. These are the four hydrogens that you had to begin with from the ethene molecule. What have you added to the molecule?
Hydrogen.
Hydrogen. You've got a hydrogen over here. You've got a hydrogen over here. What is this molecule? It should be familiar. What is the name of this molecule?
Uh,
How many carbons does it have?
2,
How many hydrogens?
6,
What is this?
Alkene.
It's an alkane. Which alkane?
Ethane.
Ethane. So we are following,
yes.
right? There is a bit of memorization and then, a lot of mental gymnastics,
Okay.
right?
Yeah.
So you need to keep up with that,
Yeah.
right? And so what you're doing over here is that, remember that when we taught that when there's at least a double bond, those are unsaturated. So an ethene molecule is unsaturated and an ethane molecule is saturated, right? Because it's all single bonds. And so hydrogenation is used for, making alkanes out of alkenes, right? If that is the purpose. Otherwise, it is used in the manufacture of margarine from vegetable oil. So manufacture of margarine from vegetable oil. So margarine is not butter, right? Butter is something you get from animal fats, right? Margarine is hydrogenated vegetable oil. Those are two very different things. Achha, what are the conditions for this reaction to take place? You need 200 degrees centigrade of temperature. Plus a nickel catalyst. All right.
What is a nickel catalyst?
Nickel is a transition metal, and a catalyst is a catalyst.
Yes.
Right? Helps speed up the reaction. Okay. Next up, right? One is hydrogenation. The other is hydration. What do you think we are adding over here?
Oxygen and hydrogen.
Right. Okay. It says hydration.
It hydrates probably water.
Yes. Good.
Oh.
Right. And that tells me you are still with us. Okay. So you are adding water to an alkene. So again, right? Water not in the liquid form, you are taking ethene plus steam. Right. So in the gaseous state. So what do we have? We've got this guy again. Plus you have H and OH. Why am I writing H2O like that? Because that's sort of how it's represented, right? H2O is represented as HOH and not as HOH. Okay,
Okay.
so it's not written like that. It's written like this. Now, this also this particular way of writing it, right? Let's call it. I mean the structural formula tells me that the water molecule is sort of broken in, it can be broken into two parts. You have only the hydrogen, and then you've got an oxygen plus hydrogen. So seeing this and what we just did over here, in this case was easy because it was just hydrogens. If I draw this out, right, again, so we're going to lose the double bond, right? We've got the two hydrogens over here. And what are we adding, you know,
Hydroxide.
hmm?
Hydroxide will not be written separately, no?
No. So, right, what do we have? What do we add?
H.
So you've got a hydrogen over here, which is this guy.
And OH on the other side.
Yes. And you know what this can you guess the name?
There are 6 hydrogens.
How many carbons are there?
2.
Right, so it's going to be eth something.
Ethanol. No.
Yep,
Oh.
it's an alcohol, ethanol. Right, the functional group of alcohols, we'll do that in the next chapter. The functional group of alcohols is the OH. Right, and in this
Okay.
case, Haram, it's not called the hydroxide but the hydroxyl group, which is the functional group. So during reactions of alcohols, this is the guy taking part in the reaction.
Okay.
Okay, we'll come to that more later. So this is a second type of addition reaction. This is right one way that industrially you can get what alcohols, right, and not like the consumer alcohols, but the industrial alcohols like spirit and methanol and those antiseptics and all of this, right?
Okay.
uh, it does say that it is used in the manufacture of ethanol. Now, to my understanding, I hope I'm not mistaken, that the ethanol that they're producing is not, again, right, it's not the one that that is consumed as the general term alcohol. Okay, so the drinking alcohol, it's not the same one. It is the ethanol that is used in as a solvent or other applications.
Okay.
All right, now remember we talked about reversible reactions,
Yes.
right? So this is a reversible reaction, so the arrows would actually go this way. Right, it is a reversible reaction and the conditions are 300 degrees centigrade, right, 6,000 kilopascals of pressure, and you need a phosphoric 5 acid catalyst. So phosphoric 5 acid catalyst. Right, obviously these reaction conditions and requirements are given in the text, but just to highlight them. Okay, clear?
Yeah.
Any questions?
No.
Okay, just now there's another addition reaction that can be conducted, and this one is used as a test for the presence of alkenes, or not specifically alkenes, but test for unsaturated, let me just, a bit too untidy, unsaturated compounds, right, meaning the ones that have at least a double bond, which alkenes do, right? And what do we do? The addition reaction is called halogenation. So what do you think we're adding to the alkenes?
Halogens.
Halogens, which are which guys in the periodic table?
7, I
Group
guess.
7, right? So you got the fluorine and chlorine and bromine and iodine, all of those guys. So what's happening here is you're taking, again, let's take ethene, and you got the hydrogens, and you have, for example, bromine. Now, why are we taking bromine? Why aren't we taking fluorine or chlorine or iodine? Well, iodine is like solid at room temperature. Bromine is a liquid. And right, the problem with chlorine and iodine, if I'm not mistaken, is that the color is not as, it doesn't stand out. Right, bromine is like orange brown. You can really make out the color, and the color is important in this case, and that's why we're using bromine. So we have ethene and we've got bromine. So ethene plus bromine, and what is that going to give you?
You have to add bromine on the sides.
On the sides, with each, you have to add a bromine with each carbon in this case.
Yeah.
Right, and so that is going to give me something called, okay, would you consider this molecule to be an ethane molecule?
No.
Yes. Why would I consider it to be an ethane molecule? Because it is a 2-carbon molecule, it is saturated, it has single
Yeah, yeah,
bonds, right? So in
yeah.
principle it is ethane. The difference is it's got bromines in 2 positions rather than hydrogen. So it's not just an ethane molecule. So I can't write I get ethane, right? That would be incorrect. It is ethane, so I'm going to write that over here, but it's something else. How many bromines do I have?
2.
And for that, I will write di.
Die.
And then for the bromine, I will write bromo. Di means 2, bromo means bromine, ethane is ethane. Right?
Dibromoethane.
Yes. So this molecule is called dibromoethane. Right? This is C2H4 plus Br2, and this is giving you CH4, sorry, C2H4 Br2. Okay, now just stay with me. This is what you're getting. All right, this is called dibromoethane. The first thing, why are we using bromine? Because bromine has a orange brown. What did I just write? Bromine, right, is orange brown solution. Okay, and this is when bromine is like just bromine, right? It's just a solution of elemental bromine. Okay, Br2. When, right, there's a saturated compound, which in this case is ethene, and the addition reaction takes place, the bromine is incorporated into the molecule, into the organic molecule. What would happen is, if addition takes place, right, the solution goes colorless. Okay.
Yes.
So if you are carrying out this addition reaction and you see the color change, that, oh, it went from orange brown, which was the bromine solution, to becoming colors, that means addition has taken place, which means that the substance that you had was a saturated compound. Okay,
Yeah.
are you sure?
Yes.
I do realize that there's like a bit to take in, and you're sort of like, oh, this can also happen, this can also happen, right? You need to like process this and digest this. And I do believe, at least for the IGCSE, which is almost the same as we know, except for a few minor difference. You are IGCSE, right, Sobia? Yeah.
Mm-hmm.
So you can like get a hold of the workbook. I believe it's available for free. I think it's available for free, maybe, on the publisher's website,
Okay.
right? So you can get that, and they'll have questions, and there are obviously questions at the end of the chapters. This is a chapter for which I would highly recommend you attempt the questions first, try your best, and then look up the answers. There's also the answer booklet for the textbook and the workbook, both.
Okay.
Right, so you try it out and then you check the answers and see how well you're doing, because this one, as I mentioned, right, organic chemistry does require some level of mental gymnastics,
Okay.
right?
Yeah.
Now the dye thing, right, what does dye mean? As you can, I told you, it means two.
Yeah.
So what you need to know is mono, di,
Mean
and tri.
mono means 1, di means 2, tri means 3.
Yes, I mean there's more to it, right? There's
Qua.
quadra,
Okay. Yeah.
quadra, and penta and hexa, but you don't need to know that. It's not going to go to that, number.
Extend.
Yeah, it's not going to go to that extent. Right, penta and hexa and septa and octa and nana, and deca all the way up till 10, right? So
Yeah.
right, you need to know at least these three guys. They might come in handy, right? In certain naming, or at least understanding the name. If they throw at you something like, right, trichloroethane. In fact, no tetra as well. Oh, sorry, no, not quadra. My bad. This guy is tetra, not quadra. Quadra is used in a different scenario. Tetra, just 4. Yeah, so no tetra as well. So these 4 guys, right? And so, for example, they're saying trichloroethane, and so you're okay, fine. So ethane is 2, and trichloro means that there are 3 chlorines in there, and so one's here, and the third one you can fit anywhere you want, and the rest you fill up with hydrogens. Okay, and so that's a displayed formula, and you can go, oh well, this is CH2Cl and CHCl2, and so that is the structural formula. So just knowing that tri means 3, you can do a lot with that. Of course, right? Because it's ethane, it makes it much simpler. If this were a bigger molecule, right, then obviously you'd be like, oh, where does it go? But again, right, there'll be context in the question or some hint or something. It's not they're not going to just throw it at you randomly. But the point is, know what mono, di, tri, and tetra mean. Okay.
Yeah.
Okay. Anything left for this chapter? Oh my God,
I hope
polymers.
not.
There's the entire topic of polymers. I think it slowed down a bit, but
Okay.
yeah, no. So I'll have to deal with polymerism tomorrow. I might leave some of it where they're talking about the environmental challenges of plastics. That's mostly just reading, and so
That should be easy.
what I'll do is I'll cover the chemistry part of polymerization tomorrow, and
Sure.
I'll leave the simple reading and information. There is information for you to know, but you can just like read through it and figure it out. Okay, so I'll leave that to you. And so tomorrow the first part of the class will be talking about polymerization, and then we'll start with chapter 13 and start talking about alcohols. Okay,
Okay. Okay.
any questions about what we did today?
No, sir.
Right, it's just that I could take a few more minutes of your time, but that's not going to help with what we have to cover. So I'll even though I did intend to do that, but I think I'll just stop at this point. Okay,
Okay.
all right, I'll see you guys next time, inshallah.
Allah.
Allah Hafiz.
Allah Hafiz.
Allah Hafiz.